Okay, so this is the podcast for Introduction to the Periodic Table. This is Unit 8. And if you're interested in following along in the textbook, you can read Chapter 6, which is the Red Book. And the treatment in the Red Book is pretty well done. Okay, so first we're going to talk about the periodic law, which basically says that the physical and chemical properties of elements recur, which means occur regularly, periodically is the key word, is where we get the name periodic table. So we have Monday occurs periodically. Every 7 days we can expect Monday to occur. January occurs periodically. We can expect every 12 months for January to occur. Those are things that are periodic. And it's arranged by increasing atomic number. So as the atomic number increases as you go across the periodic table, and you have the break in the right place, you can start to see some properties line up, right? Similar properties in the groups. That's what the periodic law says. Okay. So it all started with Mendeleev. Well, actually others had tried before him. There were about 68 elements at the time that Mendeleev decided that it would be really convenient to have some way of organizing the elements in some logical way to make them more easy to work with. He was a Russian chemist. He's considered to be the father of the periodic table. He put together a table organizing the elements back in 1869. And as I said, at the time there were 68 elements, and he organized those elements by their atomic weights. In some cases, he made some slight adjustments where he would flip around two things that had weights that when put in order did not cause the properties to line up. Okay? So he did this so that the properties, once he laid out his table, so that the properties vertically in these groups would line up. Okay. So after Mendeleev put together his table, Moseley came along, and he rearranged the table in 1913, and he arranged it in atomic number order. Okay, because remember though I said that sometimes Mendeleev would switch some elements because they didn't make sense. Once Moseley put those in atomic number order, the properties lined up really very well. So why didn't Mendeleev put his table in atomic number order? Well, it's easy to answer that question because at the time the proton had not yet been discovered. So no one had the concept of atomic number or the concept of protons, and Mendeleev had was weights, so that's what he used. But the table does work better, and it's basically very similar to what Mendeleev had, but when they're arranged by atomic number, the similarity in properties lines up much better. Okay. So here's what our table looked like today. The groups are lined up vertically, similar properties. Okay. You can see the key here that shows you which groups are what. And then the periods going across represent the number of energy levels or shells with electrons. On the bottom you have the F block, which really belongs inside the table. Okay, So we can look at the table and identify where there are metals, nonmetals, and metalloids. And okay, so if you just look at the table, you can identify the metals because they are left of that staircase that's on your periodic table. And if you look at their properties, they are all silver, or mostly silver. They are high luster, which simply means that they are glossy. They are good conductors, both of heat and electricity. So for heat, that means that if you put a metal spoon in a pot of boiling water, that heat from the hot water will be conducted up the spoon into your hand if you're touching it. And it electrically conductive means that a current will run through it. And they are also malleable, which means you can hammer them into a fine sheet. They are also ductile, which means that they can be drawn into a wire. They are, with the exception of mercury, all solids at room temperature. And they tend to form positive ions known as cations. Okay, moving over to the nonmetals. They are located to the right of the stair step. And from a property standpoint, they are non or poor conductors of both heat and electricity. They are either gases or brittle solids at room temperature. They're a lot more diverse than metals are. Okay, they form negative ions, which are known as anions. Okay, and last we have the metalloids, which are located along the stair step on your periodic table. As you can imagine, they're metalloids, are between metals and nonmetals, and they have properties that are between metals and nonmetals. In particular, the conductivity is what's somewhere between an insulator and a conductor. They tend to be dull and brittle, and they are all solids. So they are, some of them are known as semiconductors. Things like, in particular, silicon has sort of revolutionized the electronics industry. And what that means is that, so they don't conduct as well as metals, but they conduct more than nonmetals. And through things like doping, where I can add a little bit of another metal, I can make them either conduct more or conduct less, which means that I can make them tailor-make the amount of conductivity that I need to make electronics work really well. And of course, silicon has a whole valley in California named after it for its wonderful properties that allows that to happen. Okay. All right, so the octet rule says that atoms react by gaining, losing, or sharing electrons so as to acquire the valence electron configuration of a noble gas. So that's why atoms bond, right? They lose electrons, they gain electrons, or they share in a covalent bond, because the goal is to get this valence, full valence shell, which of course in most elements means 8 electrons, but of course for helium it would mean 2 electrons. Okay. If you look at the periodic table, as you know, you can identify the charges that elements will take on. So for instance, if you look at group 1 and 2, they are likely to lose electrons. And remember, so this is the D block here, and when electrons are being added here, they're being added inside the outer ring. So therefore, they also have 2 valence electrons. These are the charges that will be made here with these groups. And so these elements here lose electrons to become like the noble gas before them, whereas elements on the right-hand side tend to gain electrons to become like the noble gas that follows them. Okay, so here's a skeleton of the periodic table that shows how everything is lined up, and you can see the groups in the vertical columns and the periods in the horizontal rows, and you can identify the S, the P, the D, and the F block that we learned about during the electron section. And then, of course, we have the alkali metals. We're going to talk about each of these groups. If you would like to write them in on that table, you can do that. Alkali metals are group 1, first column in the periodic table. They have one valence electron. They're mostly silver. They are so soft that they can be cut with even a butter knife. They are the most reactive metals. They're extremely reactive, and they are so reactive that you don't find them free in nature. And that's because they bond with things around them. So you're not going to go mine sodium. You're going to find sodium in sodium compounds, sodium carbonate, sodium chloride, and you get the sodium from decomposing that compound. Okay, the second group, the second column, sometimes called families because their properties are similar, is the alkaline earth metals. They are group 2. They have 2 valence electrons. They tend to be both harder and denser than alkali metals. They have a higher melting point than alkali metals. They are very reactive, but not as reactive as alkali metals. And they are reactive enough that they too are not found in nature, but rather are found in compounds. Okay, when we look at the whole D block, we have the transition metals. And remember, because these D electrons are adding inside, they too also have 2 valence electrons. They also are good conductors. They have high luster or shininess. They are harder and denser than group 1 and 2. They are less reactive than group 1 and 2. Some of those will be found free in nature. For instance, you can go copper mining or iron mining and get the metals that are not in compounds. So we're seeing a trend here that as we go across the periodic table, the reactivity goes down. So the most metallic properties are on the left of the periodic table, and the least, the trend is the more metallic properties to the left. Okay. All right, the halogens, of course, are group 17. They have 7 valence electrons. They are the most reactive nonmetals. They just need one more electron to become like the noble gas. They are very varied and diverse in terms of their how they are present. So fluorine and chlorine are gases. Bromine is a red liquid. Iodine is a beautiful dark purple crystal. And astatine is synthetic, which means it's man-made. So really very different things in that group, but all very reactive nonmetals. Okay. Noble gases, as we know, of course, are the elements in the last group. They are the most stable. They have 8 valence electrons, of course, except for helium, which only has 2. Their most characteristic property is that they are unreactive. It's sometimes called inert, which means the same thing. And they are all gases at room temperature. Okay. We have the inner transition metals. We have these, which is... Alright, so the lanthanides start with lanthanum, which is how you know you're at the lanthanides. Lanthanum, which is on the first row of the F block. So it's the top row of the F block. These are shiny metals. They are reactive, and of course they are metals. below, also in the F block, but below them is the actinides, and they start with a C, or actinium. And in this case, only the first 4 are found in nature. You can mine them. But all the others are synthetic, which means man-made. So made in a lab, usually. They are all radioactive, which means that their nucleus can undergo some change and they can become some other element, and usually by radioactive decay. So they are very unstable, and some of them are quite fleeting, like they're made and they only are there for a matter of seconds before they decay. Of course, there's an element that really defies organization, doesn't really fit in the scheme, and that's hydrogen. It's located in group 1, but of course it is not a metal, and it is a gas at room temperature. Alright, so here's the table. We can see that we have the most metallic on the left, metallic properties. We're going to, in the next podcast, learn about, I'm having a hard time writing on this, the most metallic on the left, and the most metallic as we go right. We're going to learn about what the trends are with size, as well as with reactivity. Okay, so one of the things I neglected to talk about on page 2, I'm just coming back to, is Mendeleev's periodic table. And this is what it actually looked like. And as you can see, there are some similarities, like lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine is pretty much what we have in period 2. The noble gases had not been discovered, so you don't see any of those. You do see most of the metals in group 1 listed here, although there's, like, silver is there. But one of the things he did was he left blanks. For instance, there's a blank here. And this is what led to his table being so widely accepted. He predicted that there were 3 elements that belong in the table. You know, he had his table, and he said, you know, we got all these elements, and there's an element here. I'm leaving a blank, because he said it's going to be discovered, and when it is, it will have these specific properties, and identify what the properties would be. And to everybody's amazement, within 15 years, in fact, all of the elements he predicted were discovered. So this led to wide acceptance of his table. Okay, so we're going to stop right there.